Hello friends, today I am going to discuss the dispersion which occurs in optical fiber when a laser source or light source propagates through the optical fiber for long distance, and at the output it gets distorted in the means of spreading in time domain or contracting in time domain. So why it occurs? The phenomena is known as the dispersion, and why it occurs we will go through the history and development in optical fiber. The first point I will discuss, there are so many points I have noted down here. So laser source. Second point I will discuss propagation of optical pulse through optical fiber. Third, absorption of EM wave, and fourth, Shelmier equation. So these are the throughout development. I will discuss one by one to understand the phenomena dispersion perfectly. So first point is the laser source. Any laser source emits light at some central wavelength lambda naught. Suppose that wavelength is 1.55 micrometer or 1550 nanometer. This is the communication wavelength, all over international level accepted, and the laser source has some spectral width that is called delta lambda. It may be 2 to 4 nanometer, and when the optical pulse emitted from the laser source is launched in optical fiber and it transmits some distance, at the output its frequency component get spreaded or contracted in wavelength domain as well as in time domain. So this phenomena is known as the dispersion. To know the reason of this, the development happened in the optical fiber. So they were not knowing the exact reason of this, why it's happening, why it's spreading, why the so they came to know, and they did so many experiments to understand this phenomena. One of the experiment was they launched each wavelength one by one, single wavelength. They designed first single wavelength laser source and they launched single wavelength in optical fiber, and they found what happens at the output. The there is another point, absorption of EM wave. They came to know that some wavelength, when launched on some material, that material absorbs those wavelengths. Not all the wavelengths, but some wavelengths are being observed by the material. Suppose lambda 1, lambda 2, lambda 3 are being observed at some intensity B1, B2, B3, and we know the lambda is related to the omega angular frequency, say corresponding to these three wavelengths angular frequencies are related. So Shelmier was the scientist who modeled the refractive index of this material, which depends on the angular frequency or which depends on the this observed wavelength, and it is modeled by this equation. So n of omega is the angular frequency, is equal to 1 minus summation of bj omega j square divided by omega j square minus omega square. Here omega is, this omega j is the observed angular frequency. This is the variable omega. So if you plot these things, n versus omega, what will happen? You will see something like this, and infinity going to infinity like this. Why it's going to infinity at some points? Because when omega becomes equal to omega j, so omega becomes equal to omega 1, omega equal to omega 2, means when wavelength goes to these points, this term becomes 0 and n omega becomes infinity. So what happens when n omega becomes infinity? We know velocity of light in any medium is given by the equation v is equal to c divided by n, where c is the speed of light in vacuum or free space and n is the index of refraction. So when n becomes infinity, V becomes 0. It means it is being observed completely. Suppose wavelength is transmitting from this side and some wavelength is coming out from this side, and some wavelengths are not coming at all, means they are completely observed inside. That means n becomes infinity for those. So this Selmier equation gives me wavelength dependency of refractive index. Refractive index are not same for all the wavelength, but it depends on some wavelength. So because there are some peak points, means when it returns there are some curvature. So this curvature at different wavelengths, it has different index. Now let us discuss other phenomena, other typical words related to this all dispersion to understand. Let me clean the board. So in order to develop the phenomena dispersion and its application, and its let me discuss some phenomena related to the optical fiber communication or frequency or some signal. So lambda is the wavelength, mu is the frequency, omega angular frequency, K0 propagation constant, phi is the phase, and is the index of refraction. So what is the relation among all these things? So we know velocity of light c in free space is nothing but lambda divided by time period of oscillation, and mu is nothing but 1 by t. So we can find c is nothing but lambda into 1 by t is equal to mu. So this is the important, c is equal to lambda mu. And now what is mu? Mu is equal to c divided by lambda. And what is angular frequency? It is nothing but 2 pi times frequency mu. So it becomes 2 pi, and mu is equal to c by lambda, to c by lambda. So omega is related to the wavelength lambda. Now what is K0? K0 is called the propagation constant. So suppose this all are in free space. So K0 is equal to 2 pi by lambda. It's called the propagation constant. Means it defines how much phase is accumulated when light propagates through a distance d. So it means phase, which is nothing but the angle. Like what is the phase? Let me discuss first phase, then we'll see this application of K0. Suppose this is the electric field or magnetic field of EM wave, and it propagates. So this is the complete 2 pi phase. This is pi phase, so pi by 2 phase. So this is called the phase. When it goes some distance, its amplitude may be some value depending on this angle. So these angles are called phase, and how to find this phase is nothing but kz. So k is the propagation constant. When we multiply this propagation constant with the distance of propagation, it gives me phase, and phase gives the amplitude. So how to find the amplitude of electric field or magnetic field? It's nothing but the sine of the phase. So phase gives the amplitude of electric or magnetic field, and phase is given by the propagation constant. Propagation constant is related to wavelength. Wavelength is related to angular frequency. Angular frequency is related to frequency. So all are related terms. Now what is n? N is the refractive index. People found the velocity of light in any medium is less than velocity of light in space, free space or vacuum, and they found this velocity v is equal to c divided by n. So we can find the n is nothing but the velocity of light in free space divided by velocity of light in any medium is the index of refraction. So here we discuss all the terminology because this terminology are frequently being used. So we should not miss any point. Now there is relation between angular frequency omega and propagation constant cannot. So we can write omega is equal to 2 pi c by lambda and cannot is equal to 2 pi by lambda. So if you divide omega by cannot, it's a 2 pi c, 2 pi by lambda will cancel out, it's you will find the c. So this is the another relation, c is equal to we defined it somewhere, c is equal to v into n, or c is equal to nothing but omega by cannot. C is equal to omega by cannot. So angular frequency divided by propagation constant gives the velocity of light. So what happens in any medium? If medium changes, this will change. So let me clean this. Now suppose light travels from free space to some medium, with refractive index n. What will change? Here suppose wavelength, angular frequency is omega, wavelength is lambda. So inside the medium, which is going to change, omega or lambda? So it's a lambda. Omega is the angular frequency which is related to frequency. Frequency is not going to change in anywhere. In any medium, frequency remains constant. So this is a very much important question. People can ask you in the interview. Frequency remains everywhere constant, anywhere means any medium. Why? The question is why frequency remains constant is nothing but the energy of photon we know is it's given by E is equal to h mu. Since energy cannot be destroyed or changed, so because of that, this is some superficial answer. Energy is not going to change, so frequency is not going to change. Frequency remains constant in all the medium. So it means wavelength is going to be changed. So how? We know omega is equal to 2 pi c by lambda, and it's not going to change. But c is the velocity of light in the free space. In the medium, its velocity changes. So now we can write this 2 pi c divided by n and lambda divided by n. So this c by n is the velocity inside the medium. So omega will be equal to, so it's constant, not going to change. You can see this, I have divided numerator and denominator both by n, so you can get 2 pi velocity divided by lambda by n. So this lambda by n is nothing but the lambda effective. So 2 pi v in the medium divided by lambda in the medium. So lambda in medium become lambda by n. So this is the change in the wavelength. So it contracts. Wavelength contracts in any medium by n. So now, since this is happening, we can find another phenomena also. So what happens to propagation constant in medium? So cannot was 2 pi by lambda in free space, and say k in medium is nothing but 2 pi by, so lambda becomes lambda by n here. So it's nothing but n times 2 pi by lambda, so nothing but it's a n times k naught. So we can say propagation constant k in any medium with refractive index n is n times k naught, where k naught is the propagation constant in the air or free space. So this much is again very much important equation. This equation, these equations, all these equations are very much important. Now come to the point dispersion in optical fiber. It can be maybe single mode fiber or multi-mode fiber. In single mode fiber, there are only one mode is propagating. In multi-mode fiber, more than one mode will be propagating. So due to different modes have different velocity of propagation, there will be dispersion, and this type of dispersion is called intermodal dispersion. But within the single mode, there will be some dispersion because of the wavelength dependency of refractive index, and that is called the intramodal dispersion. So intramodal dispersion is also known as the chromatic dispersion, or it is also known as the groove velocity dispersion, or it is simply known as the dispersion. So dispersion is simply known as the chromatic dispersion, and there is another type of dispersion which is due to the multimode. It is called the intermodal dispersion. There is another third type of dispersion because when light is launched either in single mode or multimode, it may be in the two types of polarization, TE, transverse electric, or transverse magnetic. Because of these two types of polarization, each polarization wave propagates within the fiber with different velocity. So there will be dispersion when both of these two, some fraction of the power goes in both of these two, the dispersion occurred is called the polarization mode dispersion. So these are the different types, and another type is the waveguide dispersion. Waveguide dispersion, and another type is the material dispersion. So both of this waveguide dispersion, material dispersion are under this. We'll study under this. So let me clean the board. So let me discuss the chromatic dispersion and the equation, how the equations are built step by step. So suppose is the optical fiber of length L, and optical pulse of laser is transmitting through this, and it reaches here after time t. So its group velocity Vg will be equal to L divided by this t. So what is Vg? Group velocity. The group velocity is the velocity of all the wavelengths, mean velocity of all the wavelengths inside the fiber, because there are different wavelengths within this packet. Each wavelength sees different velocity. So which velocity we will take as the output? So if we suppose this whole packet is propagating with one velocity, and that velocity is called the group velocity. Since in dispersion we are going to find how much time delay happens. So let this t, this side, so t is equal to L by Vg, where Vg, so t is the duration of propagation. Here we can write from this equation, and Vg, group velocity, is defined as d beta by d omega inverse. Where from this comes? So let me go to the final. I am not writing only the equation, I will give each equation's proof in detail. So what is beta? Beta is nothing but that what k I have done. Propagation constant k is also written sometime in the form of beta. So both are the same propagation constant. It's nothing but n times k naught I have derived, and it's nothing but n times 2 pi by lambda. And what is then omega? Omega is equal to 2 pi c by lambda. If you take the ratio of these two, beta by omega or omega by beta, suppose omega by beta, so it's nothing but you can find c here into c divided by n, and c divided by n is nothing but the v. So velocity of light in any medium is given by omega by beta, but this is at single wavelength, say lambda, because omega is 2 by lambda. At single wavelength velocity is given by this, but when different wavelengths propagates with different velocity, then this velocity v is nothing but derivative of omega with respect to beta, and which is nothing but inverse of 1 by d beta by d omega, or you can write this equation. So don't only write the equation, you go to the proof. Each bit must be proved. Nothing comes magically. So Vz is equal to del d beta by d omega inverse. Now, since Vz is equal to 1 over d beta by d omega, and beta is given by n into cannot, I have written all these expressions earlier. So if you are not getting, go back to this video and see all these expressions. You should able to write all these expressions, all these proofs. So beta is equal to n into cannot, or I have seen this also. So cannot is omega by c, so n omega by c. Or you can write omega by beta is equal to v. I have derived this just previously, and v is nothing but c by n. So from here also you can write beta is equal to n omega by c. Now what is d beta by d omega? So c is constant, we can take it out, and n omega, n is also suppose wavelength dependent, so it's a product term. So first we'll take n constant, and derivative of omega with respect to omega is 1 plus omega and derivative of n with respect to omega. So if n is constant, then no matter. If n depends on omega, this term is not going to become 0 or 1. So n is the function of omega. Here you can write n omega. Where from n omega comes? I have discussed in Selmier equation. N omega from Selmier equation. So n is frequency dependent. So this term will give some portion when it is multiplied by omega and added to n. So this whole value is known as the group index, group refractive index Ng. So it becomes d beta by d omega is equal to Ng by c, where Ng is equal to n plus omega d n omega by d omega. So what will become Vg group velocity is nothing but then c divided by Ng, where Ng is group index n plus omega dn by d omega. So far I have discussed this in this optical fiber. If light is launched from here and the fiber length is L and it takes time t to propagate up to here, then this Vg is L by t, and t is equal to L by Vg, length by group velocity, and group velocity is nothing but c by Ng, group index, and Ng is nothing but n plus omega d n omega by d omega, because n depends on the frequency. So this t also, t is function of Vg, Vg is function of Ng, Ng depends on omega. So t, the time delay, this time is also frequency dependent. Means each frequency reaches here at different time, and that is the phenomena, that is the term dispersion. So t, the of omega means related to wavelength, because omega is 2 pi by lambda. So this t becomes function of wavelength. So different wavelength at the input when reaches at the output have different time of propagation. Hence they spreads or they contract. Now let me derive the actual equation. So here we go for the detailed derivation of the expression of the dispersion. So t, the time of propagation, is the function of omega. We can write t equal to t of omega, angular frequency. So delta t can be written as the dt by d omega into delta omega. This is called the total derivative. Since t is the function of omega, we can write delta t by delta omega is equal to dt by d omega. So delta t is equal to dt by d omega into delta omega. So t is nothing but the L by Vg. So it becomes d by d omega L by Vg into delta omega. So d by d omega L by Vg is nothing but the del beta by del omega inverse into delta omega. So it becomes L is the constant, d by d omega, and this inverse becomes up, d beta by d omega into delta omega. So there is the second derivative of beta. So L d2 beta by d omega to delta omega. And this second derivative is known as the beta 2. So beta 2 is equal to d2 beta by d omega 2. So we can write delta t is equal to L beta 2 delta omega. So sometimes this dispersion, this delay is measured in the form of delta lambda. So we will convert this delta omega into delta lambda and beta also in the form of lambda. Let me do that. So here this delta omega and omega need to be converted into lambda. We need all the expression in the lambda form. So omega is related to lambda by this expression. Omega is equal to 2 pi c by lambda. So total derivative delta omega is nothing but derivative of this with respect to lambda. So minus 2 pi c by lambda square into delta lambda. Similarly, if you take d omega, omega is equal to this, then d omega is nothing but minus 2 pi c by lambda square d lambda. If you divide this by this, delta omega by d omega is nothing but these two terms cancels out. Here we get delta lambda by d lambda. So we can change delta omega by d omega by delta lambda by d lambda. Here we have delta omega by d omega. This can be changed, replaced by delta lambda by d lambda. So we can replace that here. So here in this expression, delta omega by d omega is being replaced by delta lambda by d lambda. So the delta t is equal to d by d lambda L by Vg delta lambda, which is given by equation d L delta lambda. L is constant, delta lambda is there. So what is this d? D is nothing but d by d lambda 1 by Vg, and this is called the dispersion coefficient d, and which can be written again d by d lambda, and Vg is nothing but 1 by Vg is d beta by d omega. And now since this d lambda we can derive from here, omega is equal to 2 pi c by lambda, d omega is equal to minus 2 pi c by lambda square d lambda. So d lambda is equal to minus lambda square by 2 pi c d omega. So this d lambda can be replaced here by this term. So it will become d omega lambda square by 2 pi c. So this expression becomes minus 2 pi c by lambda square d by d omega d beta by d omega, where this d lambda is being replaced from this value here. So we'll get this. It's a double derivative of beta, so it's nothing. D is equal to minus 2 pi c by lambda square beta 2. So this is the derivation of the dispersion coefficient. So here if we'll see, this expression becomes, this is nothing but the delay, dispersion time, how much time it gets spreaded or contracted, different wavelengths. It's nothing but d times L times delta lambda. It means it depends on the delta lambda, and delta lambda is nothing but the bandwidth of the source. Suppose laser source emits light at lambda naught central frequency, and it has some spectral width. That spectral width is delta lambda coming here. L is the distance of propagation, how distance it propagates, and D is the coefficient of dispersion. So we can find D is equal to delta T divided by L delta lambda. So its unit becomes picosecond. So this is delta T measured in picosecond per kilometer, and delta lambda in nanometer. So picosecond per kilometer nanometer is the unit of dispersion coefficient D. And this whole dispersion is known as the group velocity dispersion of chromatic dispersion. So dispersion phenomena not only distorts the signal, but it limits the bit rate. Let us understand that also. Suppose this is the bit pattern 1010, and this is the time duration of the bit TB. So this TB, the pulse broadening delta T which I have derived, this delta pulse broadening must be less than TB. If this pulse is broadening up to this, it's okay. If it broadens beyond this TB, then there will be intersymbol interference because it gets distorted. So maximum distortion should be up to this, such that it can be detected properly. If it expands beyond this TB, then there will be problem in detection. So the condition is delta t, this spread must be less than TB. So delta t must be, TB is given by 1 by bit rate b. So if bit speed, number of b bits per second is given by 1 by TB. So TB is equal to 1 by b bit rate. So from bit rate we can find the TB, and if I multiply this side, b delta t should be less than 1. This is called bit rate and time duration product must be less than 1 always to get proper detection at the output. Now if you multiply this delta t by this expression, d l delta lambda should be less than 1. This implies b into l, bl product, b into l should be less than 1 divided by d delta lambda, d delta lambda. So this is the BL product, bit rate and distance product must be less than d 1 over d delta lambda. So BL product gives me how much maximum speed you can achieve. So it's limited, its maximum value is this much because it should be less than this. So maximum value of this is 1 by d over d lambda. So there is limitation in bit rate and there is limitation in the longest distance of propagation. So you cannot, if bit rate is fixed, suppose speed is fixed 2 Gbps, then there is the limitation on L distance. You cannot propagate that much uh, data over some distance, limiting distance, because the L will be again given by 1 by b d delta lambda. So if b is fixed, Gbps speed you want fixed, that dispersion coefficient is fixed for some material, and delta lambda is the, what is delta lambda? It is the spectral width of the source. So all are fixed, then there is limitation on L. So because this is less than this, so L max should be this. You cannot propagate, transmit light beyond this length. So here I completes this. Please go through all the equation, prove all the expression, and then get some questions based on the dispersion and get back to me if you have any problem. Thank you.